right, welcome. Only reminder is that your Achieve homework is due Monday before class. And that's it. So we'll just go right into the notes. So we talked about on Wednesday solubility of different metals and different types of solids. We're going to move into talking more about the solubility of salts, so ionic compounds, and the energetics involved with dissolving an ionic compound in solution. So many ionic solids dissolve in water. If you take table salt, we're going to talk about table salt a lot. That's just a very real representation of an ionic solid that you've probably had experience with. If you take table salt and add it to water, it dissolves in the water, but a couple things are happening as someone would add salt to a water solution. So first, when you add the solid particles, even one tiny grain of salt, it has, I think, a million at least cations and anions. So adding that to the solution, those cations and anions, they're held together by ionic bonds, and those bonds have to break. The bonds between the cation and anion in the crystal. So that occurs. Also, the water has, it does have covalent bonds, but it has hydrogen bonding interactions between water molecules. When you're adding salt to the water, that's disrupting those hydrogen bonding interactions. Salt gets in between water molecules, so that disrupts hydrogen bonding interactions. And water, which has a dipole, and the ions then interact with each other through the ion-dipole attractions. This was one of the intermolecular forces. So all three of those things happen as you dissolve salt in water. So the cations and anions are solvated or dissolved in a solvent by these strong ion-dipole attractions. That's what's shown right here and over here. Partial negative oxygen dipole attracted to cation. Partial positive hydrogens attracted to the anion. Now, if you keep adding salt to the water, you'll be able to dissolve salt, dissolve salt, dissolve salt. And at some point, there's more salt present than can be dissolved in a certain amount of water. So different solids have different solubilities. But once you've gotten past the point of everything being dissolved, so once the concentration of a solute reaches the solubility, so the maximum amount of that substance that can be dissolved, a dynamic equilibrium exists. So we talked about dynamic equilibrium when we were talking about vapor pressure, or if you have a liquid in a beaker, there is also vapor pressure, which is gaseous particles of that liquid. So it's not a liquid, it's a gas right above the surface of the liquid. And when there's vapor pressure, or when you have a liquid at the surface, some of the liquid particles are escaping to become a gas, some of the gas particles are condensing to become a liquid, and those are both happening at the same time, but the rate at which a particle evaporates is not changing and is equal to the rate at which a gas particle condenses. So they're constantly converting in between the two phases, but at a constant rate so that there is a constant vapor pressure and a constant amount of liquid present. So the same thing is true if you have salt, if you have a solid in solution, some of that solid, so we're assuming we have more solid that can dissolve in a beaker. Some of that solid is becoming ions, and some of the ions are forming ionic bonds and becoming a solid. So this equilibrium arrow, the double-headed arrow here, here, and here, indicate that at equilibrium, oxygen gas, this should be O2 with a subscript, is dissolving in water and becoming aqueous. And at the same time, aqueous oxygen is evaporating and becoming gas. Or sodium chloride is breaking apart into ions in solution. And at the same time, the ions are coming together to form sodium chloride. So this occurs with substance in a solution. Now we're going to talk more about salt. So thinking about sodium chloride forming these two ions, there's energy associated with that transformation. That's on this next slide here. This is called the molar heat of solution. So delta H subscript SOLN to abbreviate solution. This measures the net energy flow resulting from those three things that I mentioned 2 slides back. So salt is added, an ionic salt is added to solution. The ions in that solid need to separate for those ions to dissolve. And ions have a certain amount of lattice energy. We briefly talked about that in Gen Chem 1. Breaking apart the ions in the solid requires energy. So that's at first, well, this middle green arrow here. We are starting from solid, salt, and pure solvent. So you've got ionic compound and solvent. And then you mix them together, and ions need to separate. That requires energy. Now we have separated ions and pure solvent. Also, hydrogen bonding interactions, we're assuming this is water, has to break. That also requires energy for these hydrogen bonding interactions to break. So breaking apart ionic bonds, breaking apart hydrogen bonding interactions. And then forming new intermolecular forces, the water molecules with a dipole interacting with ions, so the ion-dipole intermolecular force, that releases a certain amount of energy. So the delta H of solution is the difference between energy required and energy released. And that's how we get our delta H of solution. This next slide has particle pictures to describe all of this. So we've got solute interactions. So interactions between particles of the solute, so in this case sodium chloride. These have to be overcome. So the solid sodium chloride, imagine this as 1 grain of salt. The ionic bonds between sodium and chlorine, the cation and the anion, have to break. So water will come in and take off an anion or take off a cation, and that helps it, or that causes it to be solvated. But first, those solute-solute interactions have to be overcome. The solvent-solvent interactions must be overcome. So before you add the salt in, all the water molecules are hydrogen bonding with each other. When you add a grain of salt, that's disrupting some of the hydrogen bonding interactions. And then the solution can form new interactions where we have a hydrated ion, where this is sodium. Sodium is surrounded by water molecules. Chloride is surrounded by water molecules. And then we say the ions are hydrated or have solvated. So now we form solvent-solute interactions. This can result in an overall gain of energy or release of energy. So we can have an endothermic solvation process or an exothermic process. So we saw 2 slides back an exothermic graph where the sum of breaking apart ions and breaking apart intermolecular forces between the solution was less than the amount of energy released by forming the solution. So overall, we have delta H of solution less than 0. This is an exothermic process. This would release energy. If you mix an acid, a strong acid, and a strong base together, those generate a lot of heat that can make doing that very dangerous because solution can boil. But that releases a lot of heat, and so that's an exothermic process. If you do that, you'd feel heat on the outside of the beaker. You can also have an endothermic process, which remember requires energy, where the delta H of creating the mixture is less than, so the energy released is less than the energy required to break those initial interactions. And so this process requires energy. The delta H is greater than 0. An example of an endothermic solution process is those ice packs, where the ice packs contain, it's like a plastic bag, contain another bag within it. You break that releases a salt into the solution. That solution process requires energy. So for the solid to dissolve, energy is required. That takes energy from the surroundings, which is what we feel on the outside. So when you feel the cold from the ice pack, that's the energy that the solid has used to dissolve into the solution. So there's an example of endo and exothermic. Let's just put some words to this now. So an exothermic heat of solution means that the energy released through ion dipole attractions, this is solute, solvent, so solute solvent interactions, the energy released is larger than the energy required, which would be the crystal lattice energy. That's the energy required to break apart that crystal lattice. So you have a negative delta H of solution. An example is calcium chloride. If you dissolve calcium chloride, it will release energy and be warm. You'd feel that as well. An endothermic heat of solution means that the crystal lattice energy, so the energy required to break apart the crystal, is larger than the energy released when the ion dipole forces exist, so the solute to solvent interaction. So you'd have a positive delta H of solution, and an example is NH4NO3. I think this is the component in those ice packs, but I have to look that up to double check. All right. Questions so far? Okay. Then we move to the next section. We have saturated, unsaturated, and supersaturated solutions. So we'll talk about how much of a solute can dissolve in a solution and the solubility of different compounds. So we can have miscible substances that will mix with each other at any concentration. We can have insoluble substances that will never dissolve in each other. And then we can have substances somewhere in between, where a certain amount of the solute will dissolve, but once you reach that point, no more of that solute can dissolve in that solution. So a saturated solution, that word, is used to describe a solution where the maximum amount of solute has been dissolved in the solvent. So if you add any more of the solute, it won't dissolve. If you're adding a solid, it will remain a solid. So if you have a glass of water, you add 1 grain of salt at a time, you watch them all dissolve, and then at one point that next grain of salt stays a solid, does not dissolve in the water anymore, then that has passed its saturation point. The grain of salt before that was a saturated solution. Then any less salt is unsaturated. So we use the term solubility to describe the concentration of a saturated solution for a particular solvent in a particular solute at a specified temperature. So the solubility of table salt, sodium chloride, is 350 grams per liter of water. So this tells us that in 1 liter of water at room temperature, 350 grams of sodium chloride can dissolve. If you add 351 grams, 350 will dissolve, 1 gram will remain a solid. For silver chloride, its solubility is 0.0015 grams per liter of water, also at room temperature. So this is a much lower solubility. Silver chloride can dissolve in water, but only a little bit. Sodium chloride can dissolve a lot larger amount and form a much more concentrated solution. Now the solubility, notice that both of these are defined at room temperature. If you were to increase the temperature of the water, then more solid can dissolve, generally, is the trend. There are some exceptions, but we'll focus just on the trend. So generally, solids are more soluble in hot water than in cold water. We look at potassium nitrate, that's the most exaggerated difference here. At room temperature, less than 5 grams or moles can dissolve in a kilogram of water. But if we increase temperature to 80 degrees, this is still below the boiling point of water, we're at like 3 times, 4 times the amount that can dissolve in the same amount of water, just a higher temperature. So you're supplying energy to that beaker. You're supplying energy so that whatever energy is required to dissolve the substance is supplied by the heat of the solution. So increasing temperature increases solubility in general. There's an exception here, but we'll focus on the general trend, which is that solubility increases. Okay, we're gonna come back to the gas slides, but I want to skip ahead to this slide. So I think it's 2 or 3, maybe 4 slides ahead. Because this is about solids dissolving in solution, which we've been talking about, and then we'll go to gases. Okay, so we have saturated solutions, which has the maximum amount of solute dissolved at a certain temperature. Unsaturated would be any less than the solubility. But it is possible to also form supersaturated solutions. And in a supersaturated solution, the solute or the solvent is holding more solute than is normally possible at that temperature. Here's an example when you get to, if you're taking organic chemistry lab, you will do this in organic 1 or 2. This is a it's a common procedure used. We call it recrystallization. So if you have a certain amount of solid that won't dissolve in a certain amount of liquid at room temperature, you can heat up that liquid. So you heat up, let's say it's water, we're dissolving salt again. So you heat up the water, you add the solid in, so the warm water can dissolve more of the solid than at room temperature. So now you have a hot solution with some amount of solid present. And you take that beaker off of the heat, place it on the lab bench, and let it sit there and cool to room temperature. The solids will remain dissolved in the solution, but there will be more solid than can usually be dissolved in that amount of water at room temperature. So now we've passed the saturation point. There's more solid present. We call that a supersaturated solution. These solutions are unstable, and it's really easy to, we say, crash out the solid or make the solid form. So you can do that by adding a seed crystal. So 1 extra solid crystal, add that to solution, and that will cause all of the supersaturated solids, the extra solid that's dissolved, to crash out and then reform into a solid. Or you can use a spatula to scratch the side of the beaker, and that will also cause, usually, we hope, the solids to crash out of solution as well. So then at the end, we have a solution with both some solid dissolved and some solid still, or some of the, this is sodium acetate, I think. Yeah, sodium acetate. So some sodium acetate is a solid, some is a liquid. This is now just a saturated solution. The sodium acetate has dissolved to its saturation point, and the remaining sodium acetate is a solid. This is a supersaturated because we have more sodium acetate here than can usually dissolve. All right, so now we've got our learning check. We're going to do the very first part of the first question together, and then the rest you'll do as an iClicker. So let's read this. We have sodium acetate. The mass of sodium acetate that will dissolve in 100 grams of water is 119 grams at 0 degrees Celsius and 170 grams at 100 degrees Celsius. So the solubility increases with the increasing temperature. So if we have 170 grams of sodium acetate placed in 100 grams of water at 0 degrees Celsius, how much will dissolve? Well, we need to look at the solubility at 0 degrees Celsius. At 0 degrees Celsius and 100 grams of water, 119 grams of sodium acetate will dissolve. So if we add 170 grams at 0 degrees Celsius, only 119 grams will dissolve. The rest, so let's say we've got our beaker, we've got 100 grams of water, we add 170 grams of sodium acetate, 119 grams will dissolve, but we'll still have some solid at the bottom. The 51 grams that didn't dissolve are solid at the bottom. All right, so now your task is to answer the rest of these questions. Is this a heterogeneous or homogeneous solution? Is this solution saturated, unsaturated, or supersaturated? And then you take that system, heat it to 100, and answer these questions, and then cool it back down and answer those questions. And then we'll go back to the gas slides.
It's not super saturated, it's not holding you. It's just sitting in the bottom. Yeah. Oh, sweet.
No, it's not. Yeah, that's a good question. So, like, super saturated is when more is dissolved. So if you're dissolving it like 119 grams, and then the rest is solid, it just reached its saturation, and then there's nothing.
No.
It's all like 20 grams. Yeah.
So the second one is now it's okay.
All of it is dissolved. That was like.
Oh, we gotta do that. We got a while
Imagine if you see
an hour, 30 minutes lecture, the sun is supposed to move, 30 minutes in the air. No quizzes, no that. But she's so much great. If you could be explaining a whole fucking essay about the question, you still get like 4 points. Unless person she was like, what's the difference between that and the middle like top loader? No. I literally wrote a whole essay, 100-word essay about that. That's a lot. One?
the last.
It's like philosophy. Philosophy is like a whole movement. That's all
It was all small.
Well, like,
So like
That's like the only thing that I'm saying. You guys buy one as a check today or only? Next week, Friday? Oh, yeah. We got Justin,
It's more
you listen to my section?
and it's
No, it's right. What's more?
That's not fun though. Go ahead, hit it.
But it says it doesn't.
That's yeah. Man, so I think the fans will wait to dissect. One of them waiting.
Alright, I'll give you all like 20 seconds if you're still submitting. Okay, are we all in? Stop me if you're still submitting. Okay. Okay, so lots of good discussions. So this first question here, we've added 170 grams at 0 degrees Celsius. That's more than what can dissolve. So 119 grams, the maximum amount has dissolved. That means that this solution is at saturation. It is saturated. 119 grams have dissolved. That's the maximum amount that can dissolve at 0 degrees Celsius. So that's saturated. But if you look at the solution, you can see liquid and you can see solid. So this is a heterogeneous solution because it's not uniformly dissolved. We have some solid. Okay, so that's what we have first. We've added salt at 0 degrees. Then raising the temperature of that solution to 100 degrees. Question is, will the mixture be homogeneous or heterogeneous? Is it saturated, unsaturated, or supersaturated? Well, if we have 170 grams of solid in 100 grams of water that's at 100 degrees Celsius, we've reached the saturation point at that new temperature. So now at 100 degrees Celsius, all 170 grams can dissolve, and that's the maximum amount that can dissolve. So again, it's saturated. And all of it dissolves, so it's homogeneous. So it will look like this. No solid is visible. It's all dissolved in the liquid. And then we take that at 100 degrees, cool it back down to 0. Remember, the solubility at 0 degrees is 119 grams. but no crystals appear. So this means that all 170 grams are dissolved in that water at 0 degrees Celsius. That's more than the solubility of sodium acetate at 0. The solubility is 119 grams, and this is telling us that 170 grams are dissolved. So that solution, that amount of water, is holding more solute than can normally dissolve at this temperature. So this is a supersaturated solution. Oops. It still just looks like liquid in a beaker. We can't see any solid. So it is also homogeneous. So this is that solution where if you add another crystal to disrupt the intermolecular forces or scratch the side of the beaker, that would cause the solid to crash out and you'd see the 51 grams as a solid. Yeah, I can. So a saturated solution has exactly the amount of solid that can dissolve at that temperature under normal conditions. So like at 100 degrees Celsius, you can dissolve 170 grams. If you just added 180 grams to 100 degrees Celsius, 100 grams of water, 10 of the grams that you added would remain a solid. They won't dissolve. But you can go through this process of heating it up and cooling it back down to achieve a supersaturated solution. So supersaturated is like this example. You have 100 grams of water at 0 degrees, and more than 119 grams are dissolved. So more than the solubility. So you always have to look back to the solubility, which would be provided like in a table or in the statement. Yeah. Yes. So if a crystal, as soon as a crystal starts forming or that 51 grams crashes out of solution, it would be heterogeneous and it would just be saturated because it would just have 119 grams. But you're right, if one solid particle was present, it'd be heterogeneous. Yeah, good questions. Okay, let's go back to the gases slide. So now, oh, I moved mine around. Oh, we've got one more slide. I'm sorry. I keep forgetting about this one. And then to the gases. And this is all language we've already used. So a solution, call that a homogeneous mixture where all portions look the same, and these tend to form with molecule-sized particles, so really small. And then heterogeneous mixtures, they can form when you've passed the saturation point. This is when different portions of the mixture look different and tend to form with larger than micrometer sized particles. Something larger than a micrometer is like a grain of sand. If you add sand to water, that's just going to remain a grain of sand. That won't be breaking apart. Okay. Back to the gases. So now I'll give you a second to go back here. So, well, let me go back. Nonpolar gases are only slightly soluble in water, so you can dissolve these nonpolar gases. That's like carbon dioxide in soda, or oxygen and carbon dioxide in lakes and oceans. That's all necessary for aquatic life. To have a gas dissolve in water, there has to be some pressure of the gas at the surface of the water. Just like vapor pressure that can have a dynamic equilibrium with the water, dissolving a gas in water would also result in a dynamic equilibrium where some gas particles from within the liquid evaporate at the same time. Gas particles from the pressure of the gas will be captured by the liquid. So the equilibrium concentration of a dissolved gas varies with the pressure. So if you imagine adding more pressure, that's what's showing between A and B. In A, there's less pressure of the gas, so we have fewer gas particles dissolved. In B, we've increased the pressure of the gas, and that's forcing more particles to dissolve in the liquid. And then we reach, at a certain pressure, we reach an equilibrium between the two. And this is equilibrium is established when the rate of escape of the gas equals the rate of capture, the liquid capturing the gas particles. So Henry's law, which is on the next slide, relates the concentration of the gas in solution to the pressure of the gas in the atmosphere. So the equilibrium concentration of the dissolved gas in the liquid increases linearly with the partial pressure of the gas. So on the left side, these brackets here indicate concentration. So the concentration of the gas in aqueous solution at equilibrium is equal to Henry's law constant, we'll talk about in a second, times the partial pressure of the gas. Henry's law constant, it would be a provided value. This should be K with the subscript H. These are in units of moles per liter per atmosphere, so molarity per atmosphere. And KH has a different value for each combination of gas and solvent, so different gases with different solvents and at different temperatures have different Henry's law constants. So the table on the next slide has a few values, and we'll reference them for the learning check. But here's an example. So if we look at oxygen, we're going to use this on the next slide. The constant for oxygen at 0 degrees Celsius, 2.5 times 10 to the negative 3. Increase of temperature, 1.3 times 10 to the negative 3. So the constant has decreased with an increase in temperature. Less gas will dissolve in a higher temperature. And then even less, so now we're at 10 to the negative 4 at a higher temperature. These are all in aqueous solutions, concentrations in moles per liter, and gas pressure in atmospheres. So let's use that for this learning check. The Earth's atmosphere, we've talked about the atmosphere a little bit, 78% nitrogen, 21% oxygen, and then some other gases. We can use the pressure and composition of the atmosphere to calculate the concentration of each of these gases in water at standard temperature and pressure. So we're going to determine, we're just going to calculate for oxygen for time, but you could do the same process for nitrogen and carbon dioxide. We're at 1 atmosphere of pressure at 25 degrees Celsius. We want to calculate the concentration of oxygen gas in water. We need the partial pressure of oxygen gas in the atmosphere. Pressure of the atmosphere is 1 atm. The atmosphere is 21% oxygen. So we can find the partial pressure of oxygen by taking the total pressure times 0.21. So 21% converted to a decimal. So the partial pressure of oxygen is 0.21 atm. So then using Henry's law, the concentration of O2 in water at equilibrium, so aqueous and then EQ to indicate we're at equilibrium. This is the equilibrium concentration. This is equal to Henry's law constant for oxygen, 25 degrees Celsius. So going back to our table, oxygen at 25 degrees Celsius 1.3 times 10 to the negative third molarity per atmosphere. Times the partial pressure, 0.21 atm. Units of atmosphere cancels out. And so we have unit of molarity left. That's good because we're calculating concentration. If you multiply these together, 2.7 times 10 to the negative 4 molar. So we just first calculated partial pressure of oxygen and then used Henry's law to find concentration of oxygen in water at 1 atm. Questions on this one? Okay. All right, you'll have some of these practice questions on the achieve. I've got your assessments, so I'll pass them back in these last few minutes. The sound in here made me laugh. The key is already posted, so once you get yours back, take a look at the key. Ask me questions in office hours, send me questions via email, double check my math, and let me know if you have any concerns. So, alrighty. Hey.
Oh,
Oh, and I gotta stop this.
I didn't get to pull my answer.
Oh, okay.
Is there any way I can?
Yeah. Let me just stop the